Good morning, good afternoon, good evening, wherever you are. Welcome to another CIQ webinar, another Research Roundtable webinar. This week, we're going to be talking about programming trends in computing and software development. So I'd like to bring in our panel. There we go. Welcome back, guys. I think everybody's met you guys, but I'm going to go ahead and let everybody introduce themselves again. I'm going to start with you, Gary.
Yeah, my name is Gary John. I work at Lawrence Berkeley National Laboratory, manage the Scientific Computing Group, where we provide the institutional HPC for researchers. We also manage the HPC program for UC Berkeley.
That's great. Thank you. Dave.
Hey everybody, I'm Dave Godlove. I am a solutions architect at CIQ. I used to be a scientist, a neuroscientist at the NIH, and then I've been in the HPC community and also in the Aptainer community for past several years.
Thank you, Glenn.
Glenn Otero. I'm the Director of Scientific Computing at CIQ, and I've been a scientist and a cluster builder for researchers for the past 20 years. And now I'm at CIQ.
Thank you. John.
John Hanks, HPC sysadmin at CZ BioHub. Been a sysadmin for a very long time.
Thank you, John. Jonathan.
Hey, I'm Jonathan Anderson. I'm an HPC engineer with CIQ and solutions architect. I've also been an HPC systems administrator in many past lives, and I've never been a research scientist.
Thank you, Jonathan. Greg, thanks for joining.
Hi, thank you. Hi, everybody. I'm Greg. I am, founder and open source guy. It's been most of my career doing science and scientific computing.
Thank you. So let's jump into this. I know we were talking about this yesterday, and I kind of wish we could have recorded some of it because the conversation was really good and went in some ways that I didn't expect it to. But I want to start off and just ask you guys, and I'll start with you, Gary. How have you seen development in the research community change over the last 5, 10, 15 years?
Oh, boy, things have changed dramatically. We started the program here over 20 years ago at Berkeley Lab. And if we go back 15, 20 years, we were still seeing Fortran code that would run on large supercomputers like the IBM SPs, for example. And then we started to see a transition to more standardized MPI codes, a lot of closely coupled MPI codes written in C. But just in, say, the last 4 years, it's just a dramatic shift over to Python. And so that really shows up on, just the questions that we get and also how it hits the system.
Thank you. John, I'm going to pick on you now. How have you seen things change in the last 15, 5, 10 years?
A hard time getting off mute. So life sciences software really over the last 20 years moved from Perl to Python, maybe ahead of other things that moved to Python. And so there hasn't been a whole lot of shift recently as far as the languages that people are using. It's mostly R and Python for the, with R and Python wrapping a bunch of binary applications that seem to not ever change over very long periods of times. The thing that most jumps out at me on a day-to-day basis is that we're approaching a point where the number of developers is larger than the number of researchers. So it's becoming less about research and writing software for research and more about developers bringing enterprise type workload tools and stuff into the research space.
Interesting. And that's something we'll get into a little bit later, John. I'd love your take on that, but I'm going to kind of keep going around. Glenn, you've been a researcher before for a while. What have you seen change over the last 15 years?
Yeah, I'll definitely the switch from Perl to Python has been a big obvious trend. I remember being in graduate school and Python didn't exist. So a lot of things have changed for me since I was a bench scientist. I first worked on a VAX system. So all this is pretty new. Trend wise though, yeah, it's been more just Python and R, just really the higher level languages, making it easier to get work done, but not necessarily better software practices, right? I think Git has become kind of just like a band-aid for some and a crutch for others, and a way to think that their work is reproducible and transparent and whatnot. But I think that's still not taken seriously enough in the research space. Or again, just speaking for bio researchers.
Got it. Before I change topics or kind of keep diving down this hole, anybody have anything they want to add to that they've seen change? Greg, always. Absolutely.
I talk a lot, I know. So when I first really started getting into high performance computing, and I've talked about this before in our roundtables, but high performance computing meant something very specific. It was very tightly coupled, highly parallelized applications that were highly specialized for running on I almost want to say non-commodity type systems, but they were built out of commodity systems. But there was a lot of, really tightly coupled, very scalable, very large, capable applications. Now, we used to call this the long tail of science, and that the long tail of science is starting to grow and starting to increase. We're starting to see more and more different types of use cases running on these HPC systems, and I've had to redefine HPC in my own head as to what does HPC actually mean. And I went from being so specific that HPC was, this idea of very tightly coupled applications that were very scalable, to it's anything that's pretty much going to spin your CPU and generate heat. And generally, I think of it though as jobs as opposed to services. So what have we seen changed? We've seen a transformation coming from very specific applications developed for tightly coupled and parallelized runs, going and spanning now a much wider discipline of not only science and types of jobs, but just becoming much more prevalent. I never thought I would see the day in which enterprise organizations would start asking me, how do they go build an HPC cluster, right? So things have changed a lot over the past few years. So I definitely agree with the points about, some of the programming languages and whatnot changing. But I'd also say, obviously, containerization has changed as well as the interest in orchestration. We're starting to see big centers that are all of a sudden starting to talk about, how do we integrate services with our compute resources? How do we, how do we run Kubernetes? How do we integrate? I've talked to people that are like, how do we integrate VMware into our HPC stacks? So we're starting to see a very, kind of a transformation. And Al Gara, who used to be an Intel fellow, I think said this really well, which is, due to machine learning, AI, ML, compute and data-driven analytics, coupled with simulation, we're starting to see some cross-pollination, which will end up with systems of much greater capability and class. So I think that that's definitely happening. And as a result, I think the systems and the infrastructure that we are talking about in terms of building and managing and supporting these application sets is also transforming in order to better support those types of workloads.
Thank you. Absolutely, Gary.
Yeah, just to add into that, as we've seen the shift to more to Python, a lot of it is, this long tail of science. Most people think like life science codes, but it's more than that. So we'll see people in, say, for example, archaeology, who are using the HPC systems to do photogrammetry to convert 2D images into 3D. So inside of say a tomb, for example, or maybe with a patent office, they want to do OCR scanning of the patents and digitize it, but just the sheer number of patents that they want to scan makes it an HPC task. So we're seeing, it's starting to reach a lot further than I thought, than I would initially think of at first take.
It's very interesting. I didn't even
Archaeology, huh?
very cool.
Gary and I started seeing a while ago, a whole like political science wanting resources on the compute systems, library science wanting resources on the computers, and now archaeology. That's the first time I've heard of archaeology on an HPC system. That is tremendously awesome. That's
very cool. Jonathan, I know you wanted to jump in here.
Yes. So we've talked here and in other meetings about this idea of the broadening of the long tail of science and how that's affected HPC. But something I was thinking about, just as I think Gary, you were talking, was that it's also been broadening on the on ramp too, and that really leans into the Python ecosystem, where we've seen like Scientific Python, SciPy, and NumPy, and Pandas, and all of that kind of, no, I won't say supplant, but at least take over some of the use cases that people might have had to use MATLAB for in the past. And the availability of that ecosystem makes it easier for people to get in. And the applicability of that to a cloud environment also reduces some of those barriers to entry. People can come in with that same skill set, whether they were doing something small on a cloud system or on a university HPC system. But also, like, once that expectation is set and this comfort with web services and the idea that you have an interface that's backed with something more capable, where I saw that at my last position was just how much work people were getting done with Jupyter notebooks. And I presume that's inspired a lot with experiences from RStudio. And I'm really encouraged to see that on ramp open with transitions to more open code, open technologies like open source software and freely available software, and how the incentive structure around cloud computing has incentivized getting more people on-ramped more quickly. And as much as we can take that and apply it to HPC, the better we are in that space too.
Thank you, Jonathan. So Jonathan, I do have a question for you. I know we've talked about, and Greg kind of brought up earlier, we talk about containerization and more modern design pattern, that type of thing. How much are you seeing CI/CD? And if you want to define CI/CD as well, how much are you seeing that in the HPC world?
Yeah, and as we discussed, we'll broadly define CI/CD, continuous integration, continuous deployment. Basically, I would more generalize that as any kind of structure around building and testing and making your software available, rather than just I built and tested it on my local workstation. And I'll say, I saw that in the systems side. We were using that to build node images, and we talk about that a fair bit as something that we would like people to be doing with Werewolf. But I don't really have a good sense of how much that's happening in kind of that imagined graduate student research code development space. And I'd look to, frankly, probably anyone else on this panel to see if they have direct experiences with that. I know that's something that there's been a lot of value in on the enterprise side, on the web and hyperscaler side. But I'm curious if the kind of current batch of students are coming in with that expectation built in and with that framework in mind already, and as a result are building code that way or not.
Yeah, a little bit of anybody that wants to answer that, but I'll pick on Dave first, just because Dave's been in that world.
Sure. I mean, partially, partially in to answer that question, and partially to go back to your original question, how are things changing, or how have they changed in the last 10 to 15 years? I mean, I can give you my view on that, and that is, I could just kind of go through, the journey that I've taken from being an undergrad student all the way up to, where I'm at now. And I could use that to illustrate how things are changing, I think. So when I first started in undergrad, I did some research as an undergrad, and we would gather data and we would enter the data and we would bring it to the PI, and the PI had SAS, and he was like the magic person who had SAS and knew how to like analyze the data and get some statistics out of it, and we would watch him do that. And that was like, so then when I got into grad school, everybody was like, well, do you have any programming experience? Specifically, do you have any experience with MATLAB? And in undergrad, nobody had ever told me that I would need to have some programming experience to be in neuroscience, right? And so that was the advice that I used to give undergrads as a graduate student, as I was like, take some classes in programming, learn some basic programming. I think that's kind of a ridiculous advice now. I don't think you would have to go tell an undergrad, hey, you're going to have to learn how to program, because I think most undergrads who are interested in pursuing, some sort of research career are going to be aware of that. I think they're going to know that. Now, all through grad school, I didn't really have any, it was all just MATLAB pretty much. And it wasn't until I got out into my postdoc that it was like, oh, like, here, do some stuff at the shell. Here, use Bash. Here's Python. Here are some other programming languages that you need to at least be able to, read a little bit of one of your colleagues' code and understand what's going on, and so on. And then I went from there into the HPC environment, where it was like exposure to lots and lots of different languages and technologies and so on. And from the time that I started in the HPC environment, I think that we had maybe 1/4. So this was at the NIH, and we served the intramural NIH community. When I started there, I think we had about 1/4 of the scientists who were intramural on the campus who were registered to use the high performance computing cluster, the HPC systems. By the time I ended there, I guess somewhere in the neighborhood of about 6 years from start to finish, we had 3/4 of the scientists on campus were registered to use the HPC system. It used to be, when I started there, we had some staff members who would teach like Bash basics, and they had a class that was basically like Bash, and let's come in and, figure out how to manipulate files and, write to files and do stuff like that at the command line so that you can use the HPC systems a little bit. They ended up like pre-recording that class and just putting it up on the website, because it got to the point where it was like, it seemed like almost everybody that they came in to train already had some fundamental experience. And that was a shift just within the 6 years that I was there. So, I think that you can see that trajectory from, what I have to actually use a computer, all the way up to like, oh yeah, everybody who comes in here already knows how to access, basic commands and file management and stuff like that at the shell, and has some programming experience. I think that that's probably the direction in which the community is heading,
So kind of on that, David, this brings up a question for me. Thank you, Scott. Glad you enjoyed the meeting, webinar, call it whatever you want. We appreciate it. So Dave, kind of the point you made of it, people come in and they already know things. I wonder if you can attribute some of that to the readily available versions of Linux. So being able to go install Linux on a very inexpensive piece of hardware or on an old laptop, since that has become something that's been easier and easier to do as we get further away from the beginning of Linux. Do you think that contributed to that? People just have the ability because it's cheap and it's free and you can go do it on any old hardware. So maybe they show up and they have a different level.
Once again, from my own personal standpoint, that definitely helped me along, and yeah, I think that probably, Linux is becoming more and more like mainstream. People are using it more and more at home just for, they've got some old hardware and they just want to be able to use that hardware for something. And so they install Linux on it. So definitely, I think that that's helping. I think that a lot of people probably get their first entree to the command line and using shell, probably just from using Mac. Probably the Windows subsystem for Linux is also probably contributing to that as well, giving people, even who don't have maybe their own Linux system, some ability to do some basic file manipulation or some basic like just SSH, that kind of stuff at the command line. That's probably giving exposure to people. But yeah, I think that the bottom line is that users are starting off being more educated, knowing more about, not just about like how to use their computer and how to program but like the ecosystem, like GitHub and GitLab and CI/CD pipelines, what those are, what to use them for, maybe some experience with them, that kind of stuff. You're seeing, people coming in with a higher level of technical familiarity, I believe, than what we used to have just even 5 or 6 years ago.
That's great. Thank you. Alan, thank you for joining.
Yeah, sorry, I was a little bit late. I had Slack issues on a new computer.
No worries. So I'll ask you kind of what we started off with. What have you seen from a software perspective has changed over the last 15 years?
Well, certainly the big change is the emergence of cloud computing as a, not only mainstream, but even a beginner's getting started paradigm. Part of my job at the university is to make sure that administrators understand the financial trade-offs of different choices. Mercifully, this period has passed, but 2 or 3 years ago, it was very common for a new administrator to come along and ask regarding our high performance computing center, why don't we just move it all to the cloud? And me, who started a cloud research center, over a decade ago, saying, yeah, what an idea. And having to explain all the reasons. But for people getting started, there is just no better environment. You can do anything, including bringing up, clusters, very sophisticated frameworks, Kubernetes frameworks, as a newbie. Now, a different question is whether people want to do that. So here's my short list of ways to get thrown out of a chemistry professor's office. Start talking to them about your new cloud computing framework or your new compiler options or stuff like that. They're focused on their work, and so the presence of a multitude of options, I think, is a plus and is new over the last 15 years, but not all of the answer.
That's great. Thank you, Alan. So keep going down this rabbit hole. If I look, these next two questions are kind of related or one and the same. And we talked about it to some degree, but looking at the newer languages like Python and being able to bring in a much easier version of modularity, is that playing a role in it? Does it make it easier for people to get involved with? Because I know Greg is a big Perl fan. And in the past, writing Perl, and I'm guilty of this as well, I didn't use as many of the other libraries or other people's code as much as you just went and reinvented the wheel every time. You wrote your own from scratch. And now with things like Python and some of the other newer languages, go pick one of the newer ones, you don't have to do that. And it's very easy to go get other code that just works. So is that something that has helped drive people to either, I guess they could go a lot of different directions. I'll stop there. Has modularity changed things?
I have an opinion about that, but I'm very cynical about it.
No, absolutely. Please share, John.
Modularity has made it really easy to write something that does a very complicated task really quickly. But it's also made it really easy to put something that is critical to your day-to-day existence in the hands of someone who's going to walk away from supporting it, and you have no way to fix it and keep it going. So this is, I really think the modularity that Python introduces is a ticking time bomb that's going to come back to bite us at some point in the future. And anybody who has to use and manage Conda probably will not have a good argument against that.
And that's what I wanted to get to. I want to understand. I mean, I know that Alan's gone again. I would like everybody's perspective on this because I think it is interesting. And as we go, I have other questions that are related to this. So I'll go to Glenn next.
So I hadn't thought about modularity being a double-edged sword. So that's very interesting. But I do agree violently with the Conda sprawl and and how I thought it was the silver bullet, and now it seems to be just like an anchor around my neck. I've deleted environments when they fail to rebuild and update, overnight. So it's become a real two-edged sword. And so I think, as you was mentioning that, I thought about like, yeah, it's all about, the driver behind the wheel. So, we still need better programmers to kind of like, realize that and know the difference.
You were right. Conda is a silver bullet. The problem is the gun was pointed at our head.
That's right. Yeah. Yeah. I mean, when it started, I was just starting to be able to bring in R, into my environments and things like that. I just said, this is going horribly, horribly wrong. And then I started having trouble finding, anything in Python on my laptop based on, on just that alone. So it's, yeah, I mean, we're going to need an HPC carpentry class just on how to, for Conda.
Yeah, though I have to say that the Mamba team has been doing good work in speeding it up. And I heard through a Twitter friend of mine about Pico Mamba, which runs, get this, in WebAssembly in your browser.
Interesting.
So,
Is that ultimately sustainable though? Because as I understand the problem, the way in which the dependencies are solved is just like a factorial problem, which just continues to grow and grow and grow. And Mamba, I mean, really all that's doing is it's basically taking this problem, which is going to grow exponentially, and just making it run faster because it's written in C instead of Python. So, I mean, that's a Band-Aid, but ultimately, I mean, it seems like the entire system needs to be reworked.
yeah,
Do I
100%.
misunderstand that? I don't understand.
No, I think you understand it perfectly. But yeah, faster is better than slower. But redesign. Well, so there's a related issue. We've been probing dependencies and all the package management that goes around managing them. And I think in previous shows we've talked about things like SPAC and Easy Build, which try to manage dependencies. That's been a big contributor to the success of many projects here in the US. The exascale computing project essentially couldn't work without it. European projects, I think, have been helped a lot by Easy Build. But along with that has come the GitHub generation, right? Or whether you're not using GitHub, you're using some repository with now the ability to track, security dependencies within your code and to scan things. So we're in a world now where you can release containers content security scanning, but what it will find is essentially any container that's more than a microsecond old has something you ought to go fix, and are you going to do it? So to some degree, we're just moving the sand around on the beach here. It's hopefully building some sandcastles along the way.
Thank you, Alan. Dave, I know yesterday we were talking and you were kind of telling us a story about reinventing the wheel, or why not to, or why you should. And it was really an interesting story. And I would love for you to share that if you don't mind.
Sure. I mean, I've got some strong opinions about reinventing the wheel. I mean, I think that I should probably write a piece at some point, like called like "In Defense of Reinventing the Wheel" or something like that, because, for well-established things, I mean, I understand, the basic concept is easy to grasp, right? You don't want to duplicate effort. If somebody else has already done that, then, you can get a lot further by leveraging the work that they have already put into it. But I've seen in science a lot of times where people have said as justification for what they're doing, I don't want to reinvent the wheel, and taken somebody else's code and applied it for something which it was never meant to be applied for, right? I've actually seen people take my code, when I was in that world and when I was writing code, and I've like been in presentations and stuff where somebody took my software and they applied it to a problem that it was not meant to be applied to, and I've been like, oh, wait a minute, that's not a wheel, that's a blender. And you just strapped it to your car and you're running on it and it's kind of going, but it's not doing what it's supposed to. And your answer is wrong, So I think you want to be really careful about that. I mean, you really want to know, I mean, the bottom line is you can't just like turn off understanding and just say this black box is going to do what I expect it to do. You have to really know, you still have to have some level of knowledge about what this wheel is that you're doing, that you're, not reinventing and that you're using before you go and you make it, you try to apply it to your work. I mean, I used to say that it also kind of irritates me when people say I don't want to reinvent the wheel because it trivializes what people are working on. It's like we don't program wheels, we program rocket ships, that are really complicated. And these things need to be re-engineered and refactored and reworked all the time to make them better. They're not just like silly little wheels that you could program up in an afternoon, but you just choose not to because you don't want to waste the effort. These are complicated things that people have thought about for a long time. And so don't trivialize it, learn about it and work on it. And then I think that the story that Zane was talking about is I used to work in a lab where I studied the oculomotor system. And so this is the system that moves the eyes, the neural control of that and the muscle control of that. And so we tracked eye movements, and then we had software to detect eye movements called saccadic eye movements or saccades. So these are called saccade detection algorithms. And everybody was, writing their own saccade detection algorithm, which were all loosely based on, pretty much the same thing. But there were some differences in them. And my boss at the time got kind of upset about this situation and said, we got to stop. Everybody needs to stop writing their own saccade detection algorithms. We should just write the thing in C and compile it and throw away the source code and be done with it and just use that from now on. Right. And I ended up reading a paper about something called microsaccades, which are small, tiny eye movements that happen all the time, even when you're fixated on an object. And it had within it some new saccade detection algorithms to be able to more accurately detect microsaccades. And I ended up implementing that and ultimately writing a paper about it. So if we had followed, if we had just set in stone, this is the saccade detection algorithm we're using, and we had never decided to innovate on it, then, I wouldn't have been able to write a paper, and we wouldn't have gotten that knowledge in the scientific community from the research that I was able to do there. So this is my argument against reinventing the wheel. And this is also my scientific software is a little bit different. It's always on the cutting edge. It's always doing new and sometimes messy things, right? Because, you're in uncharted territory, investigating things that nobody's thought about before. And that's just kind of the way it is.
It's great. I love that story, Dave. Thank you very much for sharing. So I know we've talked about cloud. Alan, you brought up cloud earlier, and I think what I've seen, especially in the enterprise and some of very large applications that have a lot of developers a part of them, so going through a CI/CD pipeline and trying to do things very quickly, things have grown and sprawled to a place where we are now with infrastructure. And my question is, do you guys see it as it is easier for me to add infrastructure, be it cloud or any other type of infrastructure, because it's gotten to the point where it's almost commoditized, it's cheaper. Instead of fixing the code, I can just throw more resource at it. Is that a problem that we're seeing? Is that something we've enabled? Is that part of what is modularity and everything else is enabling?
Ask your CFO. Yeah, I think some people are learning experimentally the consequence of some of that thinking, or quickly running through their budgets. But there was an interesting Twitter discussion, which was recently turned into a blog post by one of the people who started the organization 2I2C, which is International Interactive Computing Collaboration, focused on things like Jupyter and Binder and executable books. The guy's name is Chris Holdgraf, and he just posted a blog summarizing why don't academic researchers use cloud services. He asked Twitter and then turned it into a blog post. Even I could be a writer with this mechanism. So no, it's actually a very nice, thoughtful take on it. So I encourage people to look for that. His blog is at predictablynoisy.com, and it's worth a dive in. And it focuses exactly on this topic. What are the consequences, financial and confusion and cost and pain involved in using cloud services. My main reason for not spending a lot of time on it in my day job is cost. Bulk computing is still far cheaper on premises, but I find it frustrating because I have this whole research center on use of cloud, and we're trying to solve the problems that Chris discusses in this blog post.
Interesting. Thank you, Alan. Greg, what do you think about cloud enabling bad code to just exist?
Well, first I wanted to go back to that Perl comment you made about me a while ago.
Hey, I'm guilty too. Not
Speaking
as
of
guilty as you are,
bad
but I'm
code.
guilty.
The duct tape of the internet.
That was awful. Hey, Jonathan gets the award for taking the biggest punch.
There was a there's another point of the double-edged sword, which is anyone who's ever, and sorry to go back a little bit, but anyone who's ever had to battle with CPAN modules, if you remember CPAN modules, to get different bits of Perl code to work, you know, when we talk about reproducibility in science, and then you start talking about the dependency hell of CPAN modules, that's a very difficult problem to overcome. Dave and I were we've always kind of gone back and forth on this, and it just came up again very recently. And Dave had another just tremendous quote on this, a good mic drop moment, where we were trying to rebuild a container or have a container rebuilt, even though the recipe file didn't change at all. Last week it worked. This week it doesn't. And that's because the internet is not reproducible. And that's Dave's quote, and I liked it. So I wanted to throw that in there. So when we start talking about all these modularity and features and whatnot in these software applications, it is definitely a double-edged sword, especially as we're talking about science and reproducible science. It is a reason to containerize in my mind. But you just brought up a really interesting question, which is, you know, does cloud kind of enable, and actually I'm blanking out on your exact wording on it, but what I got out of it was, does cloud kind of enable bad programming and or bit rot, in a matter of speaking? Containers absolutely do enable bit rot, but that's not necessarily a bad thing, especially, again, as we're talking about reproducibility in science. So, but it is, again, like everything, a double-edged sword. We have to kind of balance that out, right? So sometimes you want to have, you know, something that's maybe totally legacy, but 100% guaranteed reproducible from a software stack perspective. So if it gave you the wrong answer, you want to repeat that wrong answer. So anyway, that was my take on that. It's not really specific to cloud, but containers is definitely an enabler of cloud. So that's how I'll tie that together.
Absolutely. And the example that I was drawing from, Greg, is I worked with a group. Again, they had 400 developers developing one large thing. And they were to the point where they were throwing about 3 million errors an hour. And instead of fix the errors, it was just easier to add VMs to the environment. So we're going to continue to throw those massive amounts, but it was just easier. It got to the point where cost was cheaper I can just keep giving it VMs and add infrastructure than to go back and fix code. So I feel like at some point there is that scale of, I'm not going to go back and fix it. I'm just going to keep throwing hardware at it. It's just easier.
But that's not specific for cloud. So there's lots of situations in which in high performance computing, it's instead of optimizing your software and profiling the software, it's easier just to buy more nodes and just, you know, run it bigger or run more instances of it and break it up smaller. You know, there's been a number of situations that I can think of where optimizing the code was not, you know, even one of the top 5 priorities in terms of how are they going to make their jobs and workloads run faster.
Right. I think priorities is the right word. And here you have to, I think we have a chance to illuminate, you know, the different stakeholder communities in software performance. So if the topic is, you know, writing code, tools for writing code, we have to recognize that many HPC users many cluster users, cloud systems users are domain scientists or or business users who essentially aren't programmers, and that would be their answer typically. The difference being that with an on-prem system, you're much more likely to have a sysadmin, contact you and say, "What the hell are you doing to my file system?" Whereas, as I mentioned earlier, it'll be your CFO contacting you if it's in the cloud. So the question then, I think, is, who are the communities interested in software development, performance characteristics? We have the various C++ committees developing ever more advanced versions of that. Even GCC advancing regularly through versions. How do you connect to that community with making these things of use to users?
Absolutely. And Glenn, I know we talked yesterday a little bit, and you brought up the topic of like generalist developers versus a very specialized developer and the differences thereof. Can you kind of dive into that a little bit?
Yeah. So one of the trends I've noticed is that over the last 15, 20 years is that as domain scientists entered or started programming and using their whatever language they want, whether Perl, Python, whatnot. Over the last 10 years, particularly 5 years, research institutes and in some businesses as well, they've actually hired programmers, professional programmers, to help the researchers write better code. And so the researchers could say, "Hey, I have this problem. I'm trying to do this type of analysis. I'm doing it this way. Can you help me? I can't get it to work. Can you? But I'm spending too much time on it. I'm supposed to be, doing this stuff in the wet lab, and science is what they pay me for. So help me program this better." And having teams of those professionals in-house as essentially, a core next to, typically associated with, in the bio side with like the sequencing lab, right? Or wherever they're generating all the data. And so I've seen that as a more popular trend. The difficulty there is a couple of things. One is funding it. If you're a research university, right? Programmers cost money. They're not free like grad students, and they could also they're retaining that type of talent. It's hard to get HPC or bioinformaticians or really good programmers because you've got the unicorns of the world, the Googles and the Ubers that will pay a lot more money than research universities will. So I think it's a trend that's going to continue because people are going to want their researchers getting more done. But and it also speaks to kind of like that reinvention of the wheel. If they're going to reinvent the wheel, like let the programmer do it, not the domain scientist. So yeah, that's just a trend I've seen. If you can do it, great. If you can't, I think that's one of the reasons why the top tier institutes, whether it's the Hutch, Harvard, the Broad, Washington University, keep staying ahead, is because they'll hire actual programmers to do a lot of the heavy lifting for the researchers.
Interesting. Is anybody else seeing that? Those dedicated researchers that are there to help?
Yeah, we have at Berkeley Lab larger projects. One of the earlier questions was about whether we see people making use of CI/CD pipelines, and I see it more where the research projects engage with a group that can provide software engineering, and software engineering is a way of working. So we've taken people who were domain specialists and did programming and research, and we're really good at it. But then there's still a way of working and thinking about software. Maybe the word I'm thinking of is like sustainability, and training these people so that this way you have sustainable code. It's kind of a big thing because just because of turnover and people find out that software engineers can do things like help people look at the code and decide, okay, if I want to make it do something different, do I hack on it and fork it, or is there a better way to do this so that it can take into account upgrades down the road? I mean, there's a bunch of things like that aren't readily apparent, but what can cost you a lot later. And so we are starting to see more software engineering, recognizing it as a that some structure that could pay off.
It's an interesting topic, Gary. I don't know, John, if you had something you wanted to add to that before I ask Gary another question.
Yeah. So this is my current environment does a really good job we do a really good job of having developers that help the domain scientists. And there's a lot of overlap between development groups and the science groups where the expertise gets kind of blurred in there, but the developers do a really good job of doing what the scientists need. I wanted to add, though, that in my previous job, which was my one foray into the real world, into an actual company and not an academic research institution, I saw the exact opposite thing. And it was politically powerful groups of developers thinking they were driving the science. And it didn't work out well. And if you think about it, that's never going to work out well, because if you do HPC long enough and you do it well, you will eventually have somebody come to you and say, I need you to do this because the IT org is awful and they can't do it or won't do it or whatever. And when you put the developers in charge of the science, what you're basically doing is putting the IT org in charge of the science, and you're letting the tail wag the dog. And that's never a good thing. I don't know how to avoid it. I've lost 2 great jobs now and had to move on because a politically powerful IT org came and crushed me. But if somebody knows how to avoid that, that'd be fantastic. Let me in on that. I just throw it out there as something that happens, and it's always bad in my experience when it does happen.
So this will apply to you too then, John. And the question I was going to ask Gary is, as you have research scientists come in and work with a developer, are things like doing paired programming where you're actually pairing a research scientist to a developer so they can work together? Is that something we're seeing? I mean, that's gotten really popular, especially in Agile and CI/CD, is paired programming. Is that something that could help in this instance as well?
Yeah. I think that's the idea is a partnership, and we're thinking, because we're in an academic setting, we're thinking smaller and an extension of the project group, as opposed to a large IT organization.
John,
I'd like to jump in real quick.
Yeah, absolutely.
Sorry, I'd like to jump in real quick and say something in response too. I mean, along the same lines. So John described a situation in which the developers were kind of driving the project and were kind of moving the science in one direction. I've seen the opposite, and the opposite is that I used to work in a lab where we had hired the programmer, and what you would do is, if you didn't have time, you would take your problem to him and you would say, okay, I need data analyzed in X, Y, and Z way. And the problem was, part of programming is sitting down and breaking your problem into real steps and creating an algorithm, right? And that's part of programming. And so a lot of these folks didn't have this background to be able to do that. So they would go tell the programmer, I need X, Y, and Z. And he would program up X, Y, and Z. And he would take it back to them and they would say, oh, that does exactly what I asked you to do, but it's not actually what I wanted. Because he didn't have that context. He didn't have that scientific context to be like, oh, well, you said this, but really what you meant was that. And so that's a situation in which the scientists are driving. It's the opposite. The scientists are driving too hard the project kind of in a vacuum, not really understanding what the real necessities are from the programming standpoint. So yeah, I totally agree with you, Gary, that it needs to be a partnership. The the programmers, if that's their background, need to be comfortable with and open to learning some science and to having one foot in that world a little bit, and have to have the capability to be able to do that. And the opposite, the scientists really need to kind of meet the programmers halfway and need to be open to learning a little bit about computer science and understanding a little bit about software engineering and so on.
It definitely works best when it's a collaboration and not somebody issuing orders and instructions to the other party that's just going to blindly follow those orders and instructions.
Right. So we have the most success here when we actually present people with information. It's sort of like the rule for emails. If you're asking for help, provide information. Don't just, dump a question on someone. So we will approach researchers with output of our monitoring tools that say, hey, it looks to me like you're hammering the file system pretty hard here, but then have large periods of inactivity. Can we rebalance that? So we actually have a very extensively developed monitoring system here at my center that's kind of a research project. It's some of it's being done with industry funds to improve it. Some of it made it into the Omnia framework from Dell, for example. And it's beautiful graphics, which is what pulls people in. But what really makes it helpful is when you can say, hey, look, this is what your code is doing. We're working right now, and this stuff is not ready for prime time yet, but we're working on actually extending this instrumentation into the MPI layer of the code for some of our advanced codes. So we can go to people and say, here's something that will help. So it's an old habit of mine from way back in postdoc days when I had the job of switching people from Fujitsu Facom to VAX. And I couldn't get anyone to come to my VAX software conversion meetings until I started showing up with what we would now call pull requests saying, look, here's some code. It works. It's faster. Oh, it also happens to be VAX compatible. So, that's how you get people to change. You go to say, hey, look, this works. It's better than what you're doing now. Now, how do we get such people? So I wanted to mention the emergence of the whole research software engineering movement, and which started in the UK over a decade ago and now has become quite a mature thing. And there's an organization in the US working really fast and hard to bring up equivalent things here. It's us-rse.org. And if you've never encountered that, it's a great place to send people to who are thinking of careers in this area or looking for resources. So these are people who are in the research software engineering area and are trying to build a professional society and organization. So they have conferences. I think they're just having a conference now, and tutorials, and all the benefits of a community. So that's where you get, I think, people in the long run, is to treat it as a professional part of what we do and not something we squeeze into the corner somehow.
Great, thank you, Alan. So I think one of the themes that I've heard throughout this is general software development is not the same thing as scientific software development. They are a little bit different, or a lot different, and not just because you're good at one doesn't mean you're good at the other. That'd be a true statement.
Yeah, I think something that Dave said earlier that I've recommended this to undergraduates as he has as well, as he mentioned. Always, every science undergraduate that I've ever talked to, I've told them double major in computer science. You want to do that because if you are an average biologist, you're just an average biologist. If you're an average computer scientist, you're an average computer scientist. But you're an average biologist and average computer science, you're a unicorn. And you basically name your salary at that point. And the same thing goes for computer science, chemistry, computer science, physics, right? When you cross those two things together, that jumps somebody way up on the list of applicants for any position in either one of those areas.
Great, David, you were starting to
Well, yeah, just to hit on that. Yeah. So like, as John was saying, when I went and interviewed for grad school, they did these like crazy interviews where you would go and interview for like 2 days at one place, and you would do 1 hour for 8 to 10 hours a day with each of the PIs. And so you'd meet like everybody in the department and talk to them, and talk to them about the potential of joining their lab or whatever. And I would get questions like, are you familiar with MATLAB, or have you done any programming? And my answer to those was no. And in some cases, that was the end of the conversation. People were like, okay, well, nice weather we're having today. We've got about 45 minutes to fill. I'm going to go grade papers or whatever, and maybe you can just kind of sit there, So like, yeah, it's really important to have that background if you really want to be serious about research computing. But yeah, back to your original question, scientific software development and other types of software development are different in that I know we wish that they weren't, and sometimes we kind of like act like, well, they shouldn't be, but they are, and that's because the goals of the developers are different. If you're a software developer who's developing a tool that you want to sell, or you want just, it's open source, you want a lot of people to use it or whatever, you're going to worry about things like packaging and whether or not somebody else is able, like multiple different systems and, different environments and stuff like that. If you're a scientist who's looking to analyze some data, maybe you should worry about that stuff, but you're not. You're worried about getting your data analyzed on your desktop computer or in your HPC environment and getting those numbers that you need to put into your paper and then being done with it and moving on to the next thing. And honestly, that's what you're worried about.
Yeah,
And
that's why we have jobs, is helping such people. And to bring it a little closer to home for CIQ, of course, supporting the ecosystem that allows, migration and updating of operating systems without breaking your application base. That's where the hard work is, from my point of view, and that's a core piece of what we have to do as we migrate these applications from ancient, I won't miss the chance to say Perl code, to to something more modern.
Great, thank you, Alan. So we're coming up on time, and I want to make sure everybody gets to have a last word. But as usual, I have a last question to kind of go around with: is what do we see as next for software? And I'm gonna start at the top with Gary.
Boy, that's an interesting question. I'm one of the things that was someone just said, I think was Dave, researchers just want to get their code to work. And we're starting to see that more. There was a series of discussions here at the laboratory about the future of science and scientific labs. I mean, people are talking about things like unmanned wet labs where robotics actually do all the experiments. So that's kind of like what's in the future. But what we're hearing from a lot of people that work with scientists is that they're not going to want to know all this implementation detail. It's just too much. I mean, we're kind of at a point where people are more educated than ever before and using the systems, but now it seems like that's not what they want to do. They want to go back to something where they don't have to think about all that stuff.
Great. Thank you, Gary. Dave, what do you think's next?
Well, that's a good question. And I think that I don't really know, certainly, containerization and some of the tools that we're seeing come out are huge game changers. And we're seeing a lot, right now of the way that scientists develop and distribute code changing. I think at a more basic level, the thing that I just said about scientists wanting to just, get their code to run and that's it, and aren't concerned about some of the other, best practices and things that are important from a software engineering standpoint, come from working either in isolation or in very small teams. And when you see scientific fields begin to progress beyond what individual researchers or small teams of researchers can do and start to require bigger groups of researchers, I think that's when you're going to see researchers really start to adopt some of these procedures from software engineering, which are necessary, because that's a lot of what software engineering is. It's not writing code. It's figuring out how to write code as part of a team and with a big group of other people, and how to ultimately make sure that that code can run outside of your team, you know, with larger groups of people. And so I think that that's it's like a social change which needs to happen in order to see, you know, better programming methods take off.
Thank you, Dave. Jonathan.
So I won't make too strong of a prediction, but what I imagine for what comes next is that we have a generation of new people in the field who will come with an expectation of having functionally infinite and elastic computing available to them wherever they are. And I think that what we're going to see probably everywhere, we're already seeing in a lot of places, but what may affect research computing in the future is that expectation getting carried forward, that I don't want to have to be sitting at my terminal writing code for the HPC system to be able to get results out of it. And I've seen a little bit of that already with, you know, I've worked with a few projects that were wanting to do edge computing with drone-based projects and sensors all over Tarnation. But that kind of accessibility, one of the strangest things that I would, or what felt strange to me when we were setting up our Jupyter environment, was people wanting to be able to access it from their phone, and even more so a tablet. And I think greater accessibility to the compute resources that we have is going to, or a desire for that, is going to impact the kinds of computing systems that end up getting built, which kind of impacts the complexity and the need for that background in computing and programming that we're just going to start assuming everyone will have.
I think it's a good assumption, Jonathan. Thank you. John.
Yeah, if I look at just developers in general, you know, web developers, everybody out there, not specifically picking on research developers, I think, you know, at least like 50, 60, 70% of these people should be forbidden to ever touch a keyboard again. Like they're not helping. A lot of what comes out of this is just busy work to justify more developers. And in this weird economy that we have, which seems to refuse to take a downturn, we have this bubble where people just keep hiring developers and paying them more and more to turn out basically nothing except cycle burning stuff that, you know, converts electricity into heat. I'm really pessimistic about the software world getting better at this point. It just seems to be getting more arbitrarily complex and layered, and, you know, more interdependent. So short of a huge recession, I think we're headed for very rough times ahead.
Very expensive software.
Yeah.
Thank you, John. Glenn.
I will predict that universities will have to start having programming, like scientific programming, prereqs for some of their majors, right? So it's kind of a wish, but I think it's going to have to happen, because one thing I didn't mention is, you know, as HPC's kind of grown, it's, you know, it used to be the domain of like the physicists, right, or the astrophysicists, just the hard sciences. Well, biology has become so much more of a hard science now with all the data. You mentioned archaeology, right? Is data that were, or sciences that were considered soft now become hard. You just have this influx of scientists, and I think more and more, you know, there's going to be a need for people to be able to program as a baseline, and not just like a nice to have for your career. So that's my prediction. And hopefully they just won't, you know, turn electricity into heat.
It's a good wish.
Yeah.
Thank you. Thank you, Glenn.
Don't tell anyone I'm an optimist.
I will. Alan.
Yeah, so it's really hard to make a single prediction. I see expansion in you know, interactive, the WebAssembly direction, as we see that whole ecosystem become more powerful. You can run Fortran in your browser in WebAssembly. As I mentioned, Pico Mamba is being worked on. So I think that direction will continue. But at the same time, I believe, as I mentioned, the beginning of the of when I joined the discussion, that the ability for people to self-educate on extremely sophisticated infrastructures that used to be the domain of just experts is going to grow. You can already bring up Kubernetes clusters with a dizzying variety of single push button environments. That's going to become the norm. So you're going to see that average folks will not bother stopping at the HPCC help desk virtually or in person. They're just going to start composing these environments, and the tools to do so will become more sophisticated, partly through work of people on this call. So I'll stop there.
Thank you, Alan. Greg, what do you think's next?
So, I'm really torn on this. John's comment, it is right on, right? Software
Greg might have had to reconnect.
Software tends to grow in complexity considerably.
You're just going to have to read his mind, Zane, and say what he was.
Apparently.
Is it not working?
No, I hear you. I hear you.
Okay.
Yes,
but basically, it's growing in complexity in terms of layers and whatnot, and we're trading performance with a number of different other facets like portability, cloud native, and whatnot. And I think that's a trend that's going to continue. I don't think it's going to stop. And John, I definitely feel your pain on that, and I share it. But at the same time, I think where we need to be focused, and one of the things that we spent a lot of time on was turnkey HPC. And as we start thinking about turnkey HPC to really satisfy the needs of these broader use cases and different types of use cases, we have to be thinking about what does that look like? And that's the area where I can add value, or where I try to add value, is really thinking about that infrastructure that we need to be building and considering in terms of in terms of supporting those sorts of use cases, whether they're going the right way or not. And Jonathan wrote a message, which I couldn't stop laughing at for a little bit, which is it's software-defined heating. Even if that's the case, we still have to, it's our jobs to build that infrastructure and to support those use cases as best we can and give recommendations on how to optimize. But it's always cheaper, in my experience, to buy more nodes than to buy more people.
Absolutely. Well, guys, we are past time, and I really appreciate you guys coming today and having this conversation. I think it's always fascinating to talk to people in different parts of this world. So I appreciate it. Thank you guys for joining. Thanks for watching online. Join us next week. Go ahead and like and subscribe, and we will see you then. Thank you very much.